So next, there's a homework due on Wednesday. That homework, make sure that you give it to me online. Don't give me a hard copy, because I'm not gonna have time to grade it and return it to you. What I'm gonna do is I'm gonna upload the answers of that homework so you can have a copy, and you can have your work, you can have the correct answers, and then you can study from there. Uh, so just make sure you don't give me a hard copy, or if you give me a hard copy, make sure that you have a copy on your own so you can study. Uh, for your exam, I don't know if you know about this, but when you are doing a quiz on Canvas and you click away, so it's going to be your active window, your quiz, and the moment that you click away, it marks that you are not looking at your quiz. So if you're using your browser to look at something else, it shows. It doesn't show you what you're looking, but it shows that you're not doing your exam. Uh, so I don't care about policing students, but you guys are grown-ups and you are in college and you know how you work to be here. So I'm not gonna police. Uh, just I don't know. Just don't do things that look bad and that make me think that you are getting unnecessary help. Uh, from my experience, students cheat because they are very concerned about the grade, and they get an extra pressure of having good grades. Uh, what I can tell you is that my purpose of the exams is not necessarily to see what you don't know, but the objective is to see what progress have you how you've been doing on the material. So it's not my aim to punish you because you haven't learned X material. These things take time, and you haven't been exposed to physics in a long time, if not if it's the first time that you do it. So for your exams in general, you're gonna have, at least for this one, you're gonna have two chances. So you can do your exam, and let's say that you did a really bad exam. Don't worry. Uh, I'm gonna give you another chance. The only thing that I'm gonna ask you is that we go through your exam and let's see what mistakes have you done, and I can give you extra problems, and then you can just redo it, and then when you're ready, you can do your second try of the exam. Okay. So hopefully that will help you guys kind of release a little bit the stress. I don't feel that is a punishment. Obviously, you're gonna have your notebooks, books. You have your phone, so you can Google things. Like there's nothing I can do to prevent that. If you have with roommates and your roommate is also in this class, or happens to be a physics major, there's nothing I can do to prevent that. It's up to you. I mean, you are grown-ups. So that's it. Okay. Any questions about the exam? Any questions about homeworks? Anything? Mary? Nothing? There's another quiz that I think is due on Monday, and it's a 4-week checkup. It's not graded, although it says that it's 1 point, but it's not graded. Uh, but I just want to get a feedback from you guys to see how the classes do, and especially with this weird format that you are taking online classes twice a week and then one time in person. I'm kind of concerned to make sure that everybody's getting or understanding everything, and if there's anything that I can change and I can change it, I will. So just make sure that you fill that quiz. It's very short. There's only like 2 or 3 questions, and there's more like opinions, like what do you like, what do you don't like, blah blah blah, stuff like that. Okay, make sense? People in the chat, does it make sense? It's kind of weird. Okay, so for today, we are a little bit behind from the session in the morning, so I'm gonna try to catch up with you guys. So there are gonna be two concepts. You know what? I'm gonna one part. So one of the things that we were talking about is this idea of equilibrium and balance. And one of the things that we have said is, okay, you may have an object, any object, and that object is going to have a center of mass. And in this case, I'm going to say that the center of mass is here. If the center of mass is above the base of the object, that system is going to be in equilibrium. But if you have a very small base, like this one, now you have a very, very tiny base, then you can still have equilibrium, but it's going to be very unstable. And just any tilt of these things on either side is going to make this triangle fall. Okay. And this can apply to many situations. Now, when you have, for example, something like this, and this is the example that we've been talking so far. Well, if your supports are beyond the midpoint of the board, well, this thing is going to be stable. But if you add a box here, this box is also going to have a center of gravity. And if you try to find the combined center of gravity, if the combined center of gravity is outside the base, this thing is going to tilt, assuming that they are not bolted or anything like that. Okay, so one of the things that we want to do, one of the things that we are interested to do is trying to find out where is the combined center of gravity and compare it to the extension of the base, and then we can evaluate if something is in equilibrium or not. Okay, so this is just a very simple example. We'll do a little more complicated later, but this is a very simple. We have two workhorses. I'm going to assume that this board has a length of 3 meters, and the mass of this thing is going to be 10 kilograms. And the distance between the workhorses, I'm going to say that this is 2 meters. Okay, so from the board itself, well, you can say, well, this is 10 kilograms and it's 3 meters. I know that the center of gravity of this piece of wood is going to be right there at the center. So it's going to be somewhere around here at 1.5 meters. Okay, so the weight or the center of mass of that board is inside the base. So that system is going to be stable. That board is not going to fall, or it's not going to tilt or anything. Yeah, everyone can see that? Now, let's say that I add this box that I was talking about, and I'm going to say that this box has a mass of 20 kilograms. Now, if I put the box right at the middle of the board, well, the combined center of gravity is still going to be there at 1.5 meters, and the system is going to be stable. But as I push the board to the right, the center of mass of this box is kind of pull the center of mass of the combined object, kind of like when the guy that was doing this acrobatics was moving his legs, the center of gravity was being displaced. Something like that is going to happen. So when you add this box and you are displacing this box to the left, sorry, to the right, the combined center of gravity is also going to be moving to the right. There's going to be a limit. Either the box reaches the end of the board, or at one point, the center of gravity is going to be beyond the 2 meters, and then the board is going to fall. The ball and the board and the box are going to fall. So what I want to find out is how far can I push this thing before it falls? Make sense? Now, the way you solve this problem is by looking at that equation of the center of gravity. So the center of gravity, we said that it was x1 m1 plus x2 m2 over m1 plus m2. Okay, now I'm going to call x1 the board. So m1 is going to be 10 kilograms, and m2 is going to be 20 kilograms. So this will be the box and the beam. Okay. X1 is going to be the location of the center of mass of the beam. So this will be 1.5 meters. X2 is the location of the center of mass of the box, or the position of the box. This is what we want to find out. So we don't know this guy. Okay, and the position of the center of gravity is going to be 2 meters. This is going to be the maximum value that I can have for my center of gravity. If the center of gravity exceeds the 2 meters, the whole thing is going to tip. Yeah, makes sense? So this center of gravity can be anywhere between 0 and 2 meters, anywhere in between these two workhorses. But at the moment that exceeds a little bit of 2 meters and the center of gravity is over here, the whole thing is going to fall. Okay? So from here, I can try to solve. I'm going to solve for x2. I'm going to do it with variables first. So this is just a little bit of algebra. So I'm going to multiply quantity m1 times m2. And remember, we are trying to solve for x2. So here I'm going to have from here I can say I'm going to end up with this. And that's once I have this, I can substitute values. So center of gravity has to be 2 meters. Mass 1 plus mass 2, that's going to be 30 kilograms minus 1.5 times 10 over 20. Oops. You're going to have to ask your help. I don't have my calculator. So I have So I have 2.25 meters. Yeah.
So 2.25 is where you have your center of gravity and you won't fall, or it will?
That's where you can have your box. So this box over here, remember we are solving for x2. So this box can be 2.25 meters from the left, and the system will be stable. You push a little bit more, 2.251, and the whole thing is going to start tipping. Yeah? Make sense? Any questions? Yeah. Everything perfect? Okay. Thank you, Sarah. Okay, so one of the things that we want to talk about, Alex, questions? Oh, sorry. Okay, so one of the things that we want to talk about or one of the things that we care about these systems of equilibrium is that we want to look at the forces and torques at different joints in the human body. We want to know, for example, if you are holding a ball, or you are kicking, or you are jumping, or you are rotating, what are the stresses and what are the torques that you have at different joints. So we may have structures like this, like the arm. And in this case, what we want to find out is what is the tension on the tendon on the deltoid. There are different kind of structures, like if we want to find out the forces on the Achilles tendon, on the foot, on an ankle, or if we want to find out what is the stress on the tendon of the biceps. They look a little bit complicated, or something like this: a person holding a dumbbell above horizontal. So these are the kind of problems that we're going to try to solve. They look complicated because there are a lot of elements, there are a lot of forces, and the geometry is not very simple. But all of them have a lot of elements in common. So if you can solve one, you can solve the rest. Okay? So we're gonna start with this one. Okay? So there are a couple of dimensions that are missing. So I have 17 centimeters from the shoulder to the insertion point of the tendon, 38 centimeters to the center of gravity of the arm. I'm going to say that the extension of the arm is going to be 58 centimeters. And the mass of the arm, I'm going to say there's 4 kilograms. Okay, so you can imagine that you are doing some kind of isometric exercise. You are holding the arm in this position. Maybe you are looking at someone that went through a surgery, or someone that has an injury, and you are looking at how much force they can sustain. So we are going to add a mass here, and this mass is going to be of 10 kilograms. Yeah. Now, this structure, we have a natural pivot point that is basically the shoulder. So I'm going to set up my frame of reference here with the origin at the shoulder. Okay. So really quick, what I want you to try to do is to identify the forces that exist in that arm, all the forces that you think exist in that arm. And the people in the chat, I'm gonna try to do something. Let's see if it works. So there are a couple of things that you can do. You can write your diagram, your free body diagram, and then you can open your camera and you just put your work in front of it, and then I can take a look. Or you can take a picture and then send that picture to the chat. So that way, if you have a question, if I can take a look and see what's going on. Someone has an answer. Morgan, you have an answer. I mean, you have a question. Morgan? No? Oh, okay. Well, now you have to ask something. She clicked by mistake, so now you need to ask something. She just ignored me. They don't do that when they're in person. Okay, so try to find out what are those forces.
Hi,
How are you?
I'm good, how are you? Kayla.
You didn't do the exercise,
Yeah, I know.
so you have to do it now.
I have to do it now?
Yeah.
What was it again?
By the way, Emma is not here. Alex. My day is doing well. Thank you, Morgan. That was your question. Brian, are you there? Brian, you are there. You just decided to skip class. Emma. And Miss Grace there? They're just skipping class. Okay. You done?
I'm not really sure. I have this one and this one,
Okay.
but that's it.
So imagine you only have these two forces.
There has to be, there has to be something holding up, but I don't know what it is. I'm there with you.
Same thing. So you only have those two forces. Yes, it just.
It should have been reversed over here.
So when you're doing the free diagram on an extended object,
Yeah,
you kind of respect the locations.
okay.
So you can do those to calculate the torques. Yeah, almost. 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 Oh, wait, what's this?
Why aren't you gonna have this one of gravity?
What is this?
The weight of the arm. That was the weight of
So these two.
No.
Okay, so you are gonna have a couple of forces. So first, I'm gonna have the force of the center of mass of the arm. So that one's gonna be here, and that's going to be 38 centimeters. So this is going to be the force of the arm. That's the weight of the arm. And I think everybody got that one. Then you have the weight of the dumbbell. And the weight of the dumbbell is going to be at the edge of 58 centimeters. And this will be the weight of the dumbbell. Okay? And almost everybody got those two. Now, if you only have these two, the arm is going to fall. There has to be a force that opposes these two. So it's static. Remember, you have that the sum of the forces in X is equal to 0, and the sum of forces in Y is equal to 0. And we also going to need all the torques have to be equal to 0. Okay? We have a force here on the deltoid, on this tendon over here. And this angle is going to be 15 degrees. Okay. Now, this one is when it gets a little complicated. This force of the deltoid, it has a Y component going up, and it also has an X component pushing towards the shoulder. Okay. So if we want that force to be 0, to the forces in X to be 0, it means that we're going to have another force over here that is going to oppose the X component of this guy. Okay? And also, we're going to need a force here that helps to balance these two. Or we can assume that we may have a force over there. If you don't have a force here, you imagine that I'm putting a pencil on the wall and there's nothing there, this can fall like this. So there has to be a force, either friction or something that keeps it slipping from the y-axis. So there has to be a force here. Okay? These two, I'm going to combine it into just one single force. And I'm going to say that it's going to go like this. And I'm going to call that force on the shoulder. So in reality, we have two unknowns. We have the tension on the tendon, and we have the force of the shoulder. Okay? So I'm going to try to find those forces. And I'm going to try to find, and the way I'm going to try to find those forces is by just looking at the forces on equilibrium. So I'm going to have forces in X equals to 0, forces in Y equals to 0, and all the torques have to be equal to 0. So for each force, I'm going to have a torque. So I'm going to have the torque of the shoulder plus the torque of the tendon plus the torque of the weight of the arm plus the torque of the dumbbell has to be equal to 0. Okay. The shoulder, this force, because it goes through the origin, it goes through the shoulder, and the shoulder is the pivot point. The distance from the pivot point to this force is 0. So this torque is going to be 0. Okay. Same way that we did the workhorse problem last class, that we pick the origin where we have an unknown. Same thing here. Okay. So now I'm going to have the torque caused by the tendon and the torque created by the dumbbell and the arm. The tendon is trying to lift my arm. So this one's creating a torque that is counterclockwise. So this is going to be a positive torque. And the two weights are rotating my arm clockwise. So this one have a negative torque. Yeah? Everybody can see that? Okay, so really quick, try to find out what is the value of the tension at the tender. What is the value of this T? This is the question that you need to solve.
Is this? We don't have.
We don't have that one, that's what we don't have.
Okay. I think that.
Yeah, so this will be your extension to. There you go.
Okay, and then,
And the force, for this case, is the extension that you are trying to, that you don't know. This was gonna be an unknown.
oh, okay, so should I send it through that?
No, just write like T. That's it.
Okay, T, okay,
And for these two torques, the angle is gonna be 90 degrees. So it will be the angle between the force and the arm.
okay.
Where do you go this thing?
We have to-
Oh, sorry, this 31. Oh, this is for the, oh, okay, yeah, the.
So Holly is asking why there's no normal forces in the program. Shouldn't the dumbbell have one? So yes, technically there's a normal force between the hand and the ball. And if I were looking at the forces in the ball, I will have to include that normal force. But I'm looking at the forces at the shoulder and the arm. So that's what I'm not including that one. So you can imagine that instead of having a dumbbell on your hand, imagine that you have a really, really, really big hand for some reason. So you just have a hand that has a big mass. So you think of the hand and the ball as part of a single entity.
So I asked Grace what she said.
So she was gonna do it for last time, she was tired. But then sometimes she has meetings that go over, so that's for her study year for awesome class.
Oh, okay.
So she like has a nice meeting, so she feels like she's too late, I just watched it. Go that way, I haven't made it here.
You should have like.
Okay, I get stuck in meetings until 12, so online works best. Well, Alex said that you are very tired and you'd rather stay online, but so now you can take naps. That's what she said. But that's true. Okay, Cooper, let me see your work. The thing is, I didn't even know if they are online or not. Okay, so in this case, so the torque of the tendon, remember the equation for torque is the distance between the pivot point and the force, and I need the perpendicular component of that force, okay? So for the torque of the tendon, I'm gonna have 0.17 meters, that's R, and the perpendicular component, I don't know where is that force, so that's gonna be just T sine of 15. This is gonna give me the perpendicular component, and it's gonna be positive. Now the other two torques are gonna be negative, so it's gonna be 0.38 times the force of the arm, that would be the weight of the arm. So that's 4 kilograms times 9.8. And the dumbbell will be 0.58 times 10 times 9.8. And that's gonna have, and that has to be equal to 0. So from there, I can solve for that tension. Okay, so I'm gonna subtract everything that doesn't have the T on it. And then to solve for T, I will have to divide by 0.17 times sine of 15. Cooper, I'm still waiting for your work. I'm pretty sure he's coming. Yeah. And Kelly, what you got? Kelly?
Oh, I got,
It's gonna be a big number.
yeah, I got 421, I don't know.
421. I think it's gonna be higher than that.
Okay. I got 1,630.
1,630 newtons. This is yes.
Okay, so I was like comparing this to the one that we did on Wednesday, I think, and I don't know how to tell if I use sine or cosine with the angles, because I remember the one that we did like a couple days ago, we used cosine, and I don't know why it was cosine there and sine here.
So it's going to depend on the angle that I give you. So for example, if you have your arm, I'm going to be talking about the arm, and I'm looking at this tendon. If I give you this angle, so you're going to look, if it's the smallest angle between your arm and the tendon, smallest or smaller than 90 degrees, you're going to be working with sines. But if I give you this angle over here, so in this case will be what, 75? You will work with cosine. So it depends on what angle you get. Usually you're gonna get the first case, something that looks like this. Yeah?
I don't know. Maybe. For now, yeah.
For now, okay. Enough to keep you going? Okay, so we have a big tension, a really, really large tension for such a small dumbbell. Like even if you look at the weight of the arm and the dumbbell, you have 14 kilograms. That's gonna be 140 newtons at most. Okay, so this tension is almost 10 times bigger than that. And that's always going to be, or that's very common to see in tendons in the human body, that the stress on the tendons is going to be 10, 20 times larger than whatever weight you hold it. Like in the case of the arm, the insertion point of the tendon of the bicep on your arm is like 4 centimeters. So the tensions are really, really, really high. And one of the reasons of that is that, yes, you have big forces, but you have big displacement on your extremities. So if you think about the range of motion of your shoulder, it's pretty much 180 degrees, or even more than 180 degrees. So it's a big range of motion. And you do that by contracting a small muscle, but with a lot of force. The same way with your bicep. Your arm also can rotate almost 180 degrees. The contraction of your bicep may be a couple of centimeters. And the reason that you can have this very big range of motion is because the force on your biceps is really high compared to whatever you're holding on your arms. So this is a characteristics of the way the anatomy of the human body works. So just compensate, you trade large forces for large range of motion. Not all the muscles work like that. In the case of your head, we have a relatively small range of motion, so the stresses on the neck are a little bit lower. Other muscles or bones, they also have very, very small displacement. Okay? Makes sense? Now, we found this tension over here. Now we need to find this force, the force on the shoulder. What is the stress on the shoulder? And the way we're going to solve this is by using these two equations. The sum of forces in x equals to 0, and the sum of forces in y equals to 0. Okay? So for that, I'm going to do a free body diagram. In this case, it doesn't have to be an extended free body diagram. I can work with my regular free body diagram. I'm going to have the force that I don't know where it is. Oh, you don't have a mask. Sorry. I found out that there's one guy in the morning that has a beard. I had no idea that he had a beard. It's so weird. Like I see you in the street, I won't recognize you. Because no. Okay. Okay, so this is the force of the shoulder. Okay, I don't know where it is. I don't know what direction it's going. I don't know where is the magnitude. But I'm going to assume that the x and the y components are going to be positive. Okay, it's just going to make it easier for me to find out at the end directions and magnitudes and stuff. I have the force of the tension on the bicep, sorry, on the deltoid. That I already know that value, and I know that this degree is going to be 15 degrees. And then I have the two weights, the weight of the arm and the weight of the dumbbell, and those are going to go like this. So here I have. Okay, and I need to have these two conditions for static equilibrium. I already worked with the torque. I did whatever I can do with the torque. I don't need that one anymore. So now I have these equations. So I'm going to work with the x direction first. And in the x direction, I'm going to have the x component of the deltoid plus the x component of the shoulder. That has to be equal to 0. And this guy is going to be 1,600 30 cosine of 15 plus that is x equals 0. Negative again because it's pointing to the left. My calculator first. Can someone tell me that value, Alex?
I have 1,574.46.
Okay, so that's the x component of the shoulder. So you can imagine that that joint is pressing the bone. How do you call this bone? Which one? How do you call this bone? No, I have never taken anatomy, so I have no idea.
No,
Radius, humerus?
Humerus?
Humerus? Okay, so you can imagine that that socket of the shoulder is pressing against the humerus with this force of 1,574. Or you can say that the humerus is being compressed towards the socket of the shoulder with this force, okay? Now, we need to find the x component, the y component, and the y direction. I'm gonna have the y component of the tension plus the y component of the shoulder plus the weight of the arm and the dumbbell, and that has to be equal to 0. So this will be 1,630 sine of 15. It's going to be positive, it's pointing up. The y component of the shoulder force, I don't know why it is, I'm just assuming there's going to be positive. And the weights, both the weights are going to be negative. So this will be negative 4 times 9.8 minus negative 10 times 9.8, and that's going to be equal to 0. Okay, solving for this force, I'm going to have oh, yes, sorry, Sarah. Yes, FB is the force of the dumbbell. So I end up with negative 284.7 newtons, approx. Yeah, I can find the magnitude. Okay, I have a magnitude of 1600 newtons,
And the direction, notice I have a positive X and I have a negative Y, so it's gonna be somewhere around the 4th quadrant. So that will be 284. Okay, so that force, the force on the shoulder, is gonna go somewhere like that. That's gonna be like this. This will be the 10 degrees. Almost opposing the force of the tendon. Yeah, sure.
Why did we write it initially in the 1st quadrant and then ended up putting it in the 4th?
So first what we do is, because we don't know anything about the force, we just make a guess. And technically you can make any guess. You can think of that force to be in any of the quadrants. But from the point of view of math, it's easier if you assume that the X and the Y components are positive. Because then you know that whatever result you end up here, that's gonna give you the sign. Okay, so it's just a guess, and at the end, the mathematics is gonna tell you like, well, actually that Y component that you thought it was going to be positive, well, actually it's gonna be negative, and then with those values you can calculate the magnitude and the right direction. Okay, any other question? Taria?
I'm confused how you got the 10 degrees at all.
This is theta is going to be the arctangent of the Y component over the X component. So in this particular case, it will be like that. And actually, if you do this, you're going to end up with a negative 10. And that basically means that it's 10 degrees below the x-axis.
Okay, make sense? Yeah. Brianna? Yeah. Mary? Make sense? Okay. Over there in the chat, any questions? I'm a little bit sad that I asked you guys to put your paper in the camera and none of you did it. I'm a little bit sad. Especially with Cooper. He didn't even do it. And Grace, and Ian. I mean, Brian. So sad. They break my heart. Any questions? No? Kelly? Do you want to do any other problem?
I think I'm good.
You good?
Yeah.
Shall we go?
Yeah.
Okay. So we only have 10 positive cases so far of COVID,
14.
but 7 are cured, are out.
Does that count, that amount of COVID cases that you subtract the recovered, or
Yes.
is it?
I don't think you should track the recovery.
No, yes.
No, I don't.
No, yes. So it's a,
10 cases last week that were confirmed, and then from testing this week, by Monday, there was like 7 more.
no, so right now there are 17 confirmed cases and 7 have been recovered. So we only have 10 active cases right now. In any case, it's good. I thought we were going to be like a little higher than that. So, yay, celebrate, but social distancing. Have a good day. See you on Monday.
So I have a question about